All right, everybody. Hi, in this video, we're going to work through another example of doing a singular value decomposition, SVD, for a matrix. And so before we start that example, just want to outline the steps that we've discussed that we're going to apply to work through that example. So given an m by n matrix A, the singular value decomposition of A means that we can find orthogonal matrices U and V so that we can write A as orthogonal matrix U times some matrix sigma times the transpose of orthogonal matrix V. And so the process for doing SVD is we first compute the matrix A transpose A, which is going to be a symmetric matrix. So therefore we can orthogonally diagonalize A transpose A by finding orthogonal matrix P and diagonal matrix D so that A transpose A can be written as P times D times P transpose. So just to recall, we're going to work through this in a moment, that this process involves finding eigenvectors and eigenvalues and then constructing an orthonormal basis from those vectors. Once we've orthogonally diagonalized our product of A transpose and A, the matrix V is going to exactly be that same orthogonal matrix P from the previous step. And then this matrix sigma is going to be a matrix which consists of an R by R diagonal piece D, where the diagonals on D are going to be the singular values arranged in descending order. And then we'll have possibly some columns of zeros and some rows of zeros, so sigma has the same dimensions as the matrix A that we started with. And then lastly, we're going to go ahead and find the left singular matrix U, which is going to be an orthogonal matrix, and its columns Ui are going to depend on the singular values sigma sub I for matrix A itself, and eigenvectors for the matrix A transpose A. So let's put this process into practice with a concrete example. Okay, so now let's take a look at an example. So we would like to calculate the singular value decomposition of 3 by 2 matrix A, and it's going to be important to just note the size of this matrix, where the first column is 1, 1, 0, and the second column is 1, 0, 1. So in order to find the singular value decomposition, first, we are going to find the orthogonal diagonalization of A transpose A. So A transpose A we can calculate by taking the product of A transpose, which is first column 1, 1, second column 1, 0, third column 0, 1, times matrix A. And the result here is going to be a 2 by 2 matrix, which is first column is 2, 1, and the second column is 1, 2. So this 2 by 2 matrix, notice it's symmetric. The off-diagonal entries, they come in pairs. So the first step is to orthogonally diagonalize this matrix 2, 1, 1, 2. So we can go ahead and find the characteristic polynomial for this matrix, since we want to find the eigenvalues for this matrix. So you can verify the characteristic equation that I have below, but P of lambda is equal to lambda squared minus 4 lambda plus 3, which can be factored into lambda minus 3 and lambda minus 1. So this matrix A transpose A has two eigenvalues. The larger one is 3, and the smaller one is 1. So we have lambda 1 is 3, and lambda 2 is equal to 1. Then we want to go ahead and find eigenvectors for each of these eigenvalues. So taking lambda equals 3 first, we set up a matrix where we're going to take A transpose A and subtract 3 from each of the diagonal entries. So subtracting 3 from 2 gives us minus 1. We still have a 1 here. We have a 1 here. And then I subtract the eigenvalue 3 from this other diagonal entry. That gives me a minus 1 over here. And then I solve the corresponding homogeneous equation. And in this case, we get a solution that as long as x1 is equal to x2, this is going to be a solution to the homogeneous equation. So an eigenvector such as v1 equals 1, 1, that's going to be one possible eigenvector for the eigenvalue lambda 1 is equal to 3. Then we find an eigenvector for lambda 2, which is equal to 1. So now we're going to subtract 1 from each of the diagonal entries of our matrix A transpose A that we had up top. So subtracting 1 from the first diagonal entry gives me a 1. Subtracting 1 from the other diagonal entry also gives me a 1. And now we solve this resulting homogeneous equation, which has the solution x1 is equal to minus x2. So for example, one such eigenvector for lambda 2 equals 1 would be the vector v2, which is minus 1, 1. So now we've got eigenvectors, two different eigenvectors for each of the eigenvalues. And because these two eigenvalues are distinct from each other, notice these two eigenvectors are orthogonal to each other. So that's great. As we're going through this process, this matrix P that we construct is going to be made up of these eigenvectors, but we want to make sure that we first make sure that the set of eigenvectors is orthogonal, and then we normalize it. So the orthogonal piece is done. We don't need to do Gram-Schmidt. We just need to normalize it. Okay, so step 1, that's probably the trickiest step, which is finding the orthogonal diagonalization of A transpose A. We are just about done with that step. To find the matrices V and sigma, I just need to normalize these eigenvectors. So notice that, again, these two eigenvectors are orthogonal because they have distinct eigenvalues, but they don't have unit length. So I divide V1 by its length, which is square root of 2. I divide V2 by its length, which is square root of 2. So the orthogonal matrix V, which is going to be what we multiply on the right by the transpose of V, that is going to equal the matrix, which has first column 1 square root of 2, 1 square root of 2, and second column minus 1 square root of 2, minus, 1 square root of 2. So the columns of this matrix are orthogonal to each other, and the lengths of each of these columns are 1. So V is an orthogonal matrix. Next, we can identify the matrix sigma. And so since the matrix A that we started with over here was a 3 by 2 matrix, the matrix sigma that we construct should also be a 3 by 2 matrix. The diagonal piece we get by finding the singular values. So the first singular value is square root of 3. The second singular value is the square root of 1, which is 1, and then we have 0, 0. So this piece goes right here, and that's this chunk right here. So that's this 2 by 2 diagonal matrix whose diagonal elements are the singular values of matrix A. But because this matrix sigma needs to have the same size as the matrix A that we started with, we need to add one more row below this diagonal part. So we add one row of 0 and 0. So now this matrix sigma is also a 3 by 2 matrix. The first column is first singular value square root of 3, 0, 0. The second column is 0, 1, coming from the square root of the other eigenvalue, and then 0. So what's left to find now is the other orthogonal matrix U that we multiply on the left. Okay, so far we've done a lot of the heavy lifting. We found the orthogonal matrix V that we're going to multiply by the transpose on the right, and we found this matrix sigma. And so what's left to find is the orthogonal matrix U that we multiply on the left. And for each non-zero singular value sigma sub I, we can find one of the columns of matrix U using this formula that the ith column of matrix U equals 1 over the ith singular value times A times VI, okay, where VI is denoting the ith column vector of matrix V that we found prior. Okay, so to find the columns of matrix U, then we need to know the singular values, which we have organized in sigma, and we need to know the vectors v1, v2 that we've organized in matrix V, and then we have our matrix A, the 3 by 2 matrix that we started with. So we can go ahead and solve for U1 by taking 1 over sigma 1 times matrix A times the vector v1, and simplifying that gives us a column vector with 3 entries. The first entry is the square root of 2/3. So both the 2 and the 3 are under this square root if it's not clear. 1 over the square root of 6, 1 over the square root of 6. So here's the first column that we're going to need in this matrix U. Then for the second column for U2, we do a similar calculation. U2 is going to equal 1 over sigma 2 times matrix A times the vector V2. And simplifying this product gives us a column vector with 3 entries. The first is 0, the second is -1 over the square root of 2, and the final entry is 1 over the square root of 2. So this is great. We don't have any other singular values or eigen columns of vector of matrix V. So as far as we're concerned, we found U1 and U2, and there's no other columns of U to find using this relation. So this means we can take matrix A, and we should be able to write it as a product of a matrix U times a matrix sigma times V transpose, which I've written out here. So here was the first column of U, the second column of U. Here was the matrix sigma we found earlier, and here's the transpose of the matrix V that we found earlier. And if you're looking at this product, maybe something looks weird to you. This first matrix that we have, right, this is a 3 by 2 matrix. And this second matrix, sigma, is a 3 by 2 matrix. And this last matrix is 2 by 2. And so this product, as we've written it right here, of U times sigma is not defined. And that's because this matrix U, this has to be a 3 by 3 matrix. And we've only got 2 columns, U1 and U2. So that means we need to find a third column for this matrix U. So we are just about done, but not quite. So this would not be the correct answer. We still have a U3, a third column of this matrix U that we need to identify. All right, so now we're in the home stretch. One last task to do. So we found 2 out of the 3 column vectors that we're going to need for this left matrix U that we identify. So we need a third column, and that third column needs to be orthogonal to the first 2 vectors that we have identified. So we can solve for finding this third column by considering the following conditions, and that is if I take the dot product, I'm going to call this third vector that we're trying to find Z. And so whatever this vector Z is, when I take the dot product with U1, we should get 0. When I take the dot product of that with U2, I should get 0 because Z is going to need to be orthogonal to those first 2 vectors that we've identified. So this gives us the following system of 2 linear equations. So taking Z, which we're going to just denote as Z1, Z2, Z3. If I were to take the product of Z transpose and U1, I would get the equation the square root of 2/3 times Z1 plus 1 over the square root of 6 times Z2 plus 1 over the square root of 6 times Z3 needs to equal 0. This is going to make vector Z orthogonal to vector U1. And similarly, we get a second equation by setting the condition that we want Z to be orthogonal to U2. So that's going to tell us that 0 times Z1 minus 1 over the square root of 2 times Z2 plus 1 over the square root of 2 times Z3 also should equal 0. So we have a homogeneous system of equations, so we can set up the corresponding matrix equation to try and solve this. And so we can take this matrix, do some row operations, and write it in its reduced row echelon form, which I will write above. And so that reduced row echelon form has the top row, which is 1, 0, 1, and the second row is 0, 1, minus 1. And so from this reduced row echelon form, we can find the solutions to the homogeneous equation. These are not unique. We have a free variable, z3 is free, but what I can see is z1 is going to need to equal minus z3, and z2 is going to equal z3. So one such vector z that satisfies these conditions, for example, would be the vector z is equal to minus 1, 1, 1. And you can check that this vector z is indeed orthogonal to u1 and it's orthogonal to u2. When I take the dot product of these two vectors, I get 0. Taking the dot product of u2 and z, we get 0. So we've gotten a good solution to this system of linear equations above. And this is not, however, a unit vector. So this vector z that we found, it has a length of square root of 3. So in order to make that a unit vector, we're going to divide each of the components in the vector z by 1 over its length, the square root of 3. So our third column vector for u, therefore, is going to be minus 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. And so now this third matrix that we were trying to find u and v, these are going to be square matrices. So u had to have a third column. U was a 3 by 3 matrix. We found the first two using the formula that we have for finding the ith column of matrix u, but we were one column vector short here. So we had to find a third vector, which was going to be orthogonal to these first two and has a unit length. And that gave us this third column. So now our matrix u consists of the first column is u1, the second column is u2, and now we've found the third column, which is u3. All right, we are done. Let's just summarize the final solution on the last slide. All right, so you've made it this far, and we have finally succeeded in finding the SVD, this singular value decomposition for matrix A. So recall that that singular value decomposition means we should be able to take this matrix A and write it as a product of three matrices, an orthogonal square matrix U times this matrix sigma that's going to contain some information about the singular values of matrix A times the transpose of another orthogonal matrix V. And so since we started with a 3 by 2 matrix A, it's important to note that this matrix U, the first square matrix, is going to be 3 by 3. The matrix sigma has the same size as matrix A, so that's a 3 by 2 matrix. And then the orthogonal matrix V, we're going to multiply by its transpose. That's going to be a 2 by 2 matrix. And checking these products, everything's going to work out nicely so that we'll wind up back with a 3 by 2 matrix. So due to our previous work, we found that the matrix U was this 3 by 3 matrix. We had this matrix sigma, which had the singular values for matrix A. And then we took the transpose of our matrix V to get the right singular matrix. And so here is the singular value decomposition for this matrix A into a 3 by 3 orthogonal matrix times a matrix with the singular values times the transpose of a 2 by 2 orthogonal matrix.